Thanks a lot. Thanks to the organizers for organizing this great workshop. I'm going to talk about discreteness of asymptotic tensor ranks, and this is a joint work with Briet, Christandl-Gesmundo, Lee, Stuka, and myself. What do? We prove a new result about tensor parameters that are amortized or regularized over large tensor powers, and these we often call asymptotic tensor parameters. And
will you explain the red words?
No, these are just words. But I will explain. This is yes, this is what it looks like. So these parameters are of the following form. You have some parameter of interest, f, some function that you apply to your tensor. And what you plug in is your tensor to some large power n, apply your function, take the nth root, and let n go to infinity. So that's what I mean by asymptotic parameter or amortized or regularized parameter.
So it can be anything, or it's some kind of nice function.
We will look at some specific families.
Quantitative talk.
Yeah.
So
but
entanglement of formation or so.
That might, you might try to use
Let's do that kind of stuff in quantum too.
Sorry, entanglement cost, not a formation cost.
Yeah.
Something like that. Okay.
So, and when you do this for your function f, you call it f twiddle. Okay, that's the general notation. Now, so these kind of parameters, they play a central role in several fields. Algebraic complexity theory is one of those fields that I've worked in a lot. Quantum information is something where you will find this. And in combinatorics, this is also used a lot, either as a tool or as an object of study. We will see some of these later. Now, unlike matrix rank, for example, these asymptotic tensor parameters, they may attain non-integer values. Okay, so they may take very strange values, some strange real values. And this raises the question, which we're going to talk about a lot more. For a given f, what values can this f twiddle take when we vary the tensor that we put into it over all tensors? And so we just want to know what are the values that such a parameter can take for fixed f. If we look at all those values, we want to know, are there like gaps between the values, or do you have accumulation points so that you're like converging, or is the set of values that such a function takes, is it a discrete set? Okay, so these are some of the things you could imagine, some structure you could see.
Is it even known that it's not finite?
Well, it depends on your function, maybe. But when the functions we're going to look at will be that you will have infinitely many values.
If the function is additive, nothing happens.
If f is additive, you mean? Yeah, but we're varying over all tensors t, huh?
Wait, but tensors t of fixed order but not
so
fixed
the
dimension.
order. So you should imagine order 3,
Fixed but not the dimension.
but the dimensions can be arbitrary. So we're going over infinitely many dimensions.
Yeah, but I mean, if f of t tensor s is f of t times f of s,
then you can still get infinitely many values for your f twiddle. So f twiddle equals f. That's what you're saying. That's fine.
Yeah.
But even matrix rank takes infinitely many values, right? just all the natural numbers. But those we understand. So that's an example where it's discrete. But for tensors, weird things could happen. So our result is that we prove for several parameters and several regimes that the set of possible values is indeed a discrete set. So it means that we're in this situation. So it's gapped, but in particular it's always gapped. So you get gaps between all the values. Okay, so that's the general kind of result. Of course, I need to explain like what are these parameters and what are these regimes. Okay, so I have 5 parts. I'm going to talk about asymptotic ranks, some important examples, some applications, and some context. Then I will talk about, for a specific collection of such parameters, we know actually the smallest values that they can take, so I will talk about that. And then I will talk about the discreteness theorem. So that says that actually all the values are discrete. It's a discrete set. I will then talk about some proof ingredients. I won't give any full proof or anything. And finally, I will just state a slightly more general result to give some overview. All right, so I will start with explaining asymptotic ranks of tensors and applications, but let me start first with matrix rank, which we all know very well, so that's a good start, I think. So let's take a matrix, which is just this square in which we put numbers, and there's two ways of thinking about matrix rank. First way is we decompose our matrix as a sum of rank 1 matrices, right? And then we just need to know what is the smallest number. What is the most efficient way in which I can do this? So I try to minimize this number R. That gives me the matrix rank, right? The other way is through Gaussian elimination. What you try to do is you take linear combinations of the rows and the columns of the matrix, and you try to get your matrix into diagonal form. Yeah? And then you try to maximize the number of non-zero items, non-zero elements on the diagonal, and that's also the rank of the matrix, right? These are two ways of thinking about matrix rank, and gives the same. Here we're minimizing, here we're maximizing. That's kind of interesting, but it gives the same number in the end. Good, so that's matrices. This, we understand. Matrix rank has very nice properties, easy to compute, it's multiplicative, etc. Okay, now we go to tensors. So I'm going to talk about several notions of tensor rank. So we start with a tensor, which here I just have it as a cube, which I fill with numbers. The first notion of tensor rank is simply called tensor rank, and it follows this principle of decomposing your tensors into rank 1 tensors. Yeah? So I have my tensor T, I write it as a sum of rank 1 tensors, simple tensors. The most efficient way in which I can do this is measured by this number R. That's the tensor rank, if you minimize that. Now, I can also try to do this Gaussian elimination approach that we can do for matrices. So Gaussian elimination into a diagonal tensor. So here, what you're allowed to do, you're given your tensor, you're allowed to take linear combinations of the slices of the tensor in the 3 directions that you can do this, such that you end up with a tensor that is diagonal. So it only has non-zero elements on the main diagonal. And again, you count how many non-zero items are there, and that you try to maximize. That's called the subrank. We've seen this before. JMF has talked about it. We've heard it another time.
So Gaussian elimination means you subtract slices from each other?
Yeah, you just take linear combinations. Yeah, subtracting or...
But of whole slices?
Yeah, of slices in the 3 directions.
Or 3 directions.
So meaning you just apply linear maps to the 3 legs of your tensor. That's what it is. Yeah. Good. The last one is called slice rank. This was popularized in combinatorics. And
By someone at UCLA.
oh yeah, but Terence Tao, he came up with this, actually. That's right. To solve, to give another proof for the capset problem. How's this defined? It's a bit of a, well, it's kind of a relaxation of the tensor rank in a way. Here what you're trying to do is you're given your tensor T. Again, you are allowed to take linear combinations of your slices. This time they have to be invertible. And you're trying to get your tensor in this shape where this is the support. So you get this little cube over here is 0. You're trying to create this 0 cube over here. That is as big as possible. Yeah, so you're trying to, in other words, you're trying to minimize A, B, and C, like their sum, actually. That's called the slice rank. That's a parameter with a lot of applications. We'll talk a bit about it in a moment. Okay, so there's these 3 functions, yes?
Okay, so another way to think about the matrices is just, the number of non-zero singular values within SVD. And can you remind me of what, how the SVD fits in with the, successive SVD? Does that get you any of these, or what?
I'm not sure, but I normally don't use SVD. This also works over all fields, what we're doing here, but you could do it for complex numbers.
Also, this is invariant under arbitrary change of bases. For SVDs, or you have a distance function that you're using.
Yeah, so
non-unitary changes.
Right.
Okay.
You're allowed arbitrary invertible changes of bases, like in Gaussian elimination.
Yeah, but you could try to use it, yeah, but it's not yeah, maybe not one of these functions. Yeah.
I'm a little confused about the second method. So the second definition. So with matrices, you can guarantee you can get to diagonal form
Yeah.
from transformations on either of the axes that don't talk to each other as separable. But on tensors, my intuition says that you cannot do that, right? Like
Yeah.
with
You cannot always fully diagonalize your tensor.
right.
That's
so
right. So I
how do
allow
we define it
here
then?
these when I say Gaussian elimination here, it's in quotation marks. These linear combinations don't have to be invertible. So they're just linear operations that you apply. So you will, in general, you will lose something. That's right. Generally, you cannot go back here. Here you don't lose anything. Right? This is just a decomposition. Yeah. Another way to say, yeah, these numbers, tensor rank and subrank are different. Turns out. So your intuition is right. Yeah. Yes. So you lose something here, in some sense, but still it's useful. You can still do something with it. Yeah. Yeah. Okay. Any more questions? Good. So these are our important parameters. But we take the asymptotic versions of this, right? I take the asymptotic rank. So I have my notion of rank. I can take the asymptotic rank, which is this regularization, as I call it. Take the nth power of the tensor, apply f, nth root, let n go to infinity. Okay. So,
Sorry, but
yeah.
when you say tensor power there,
yeah.
you're really doing Kronecker power.
Yeah, it's like a Kronecker power. So you should think of T as a tensor of order 3. And when I take powers, it stays a tensor of order 3. Okay? But the dimensions go up. Yeah, that's the kind of power we're talking about. It's a tensor power of order 3 tensors. Yeah. Or Kronecker power. Just like you can do that with matrices, right? You can take a Kronecker power of matrices. So, well, this is kind of self-explanatory. I have these functions. I have their asymptotic versions, which are named like this. Asymptotic rank, asymptotic subrank, asymptotic slash rank. All right. Why are these so interesting? So let me talk about a couple of connections or applications. The asymptotic tensor rank, in the context of quantum information, you can think of it as it's measuring the rate at which some tripartite pure quantum state T can be obtained from the GZ state. The GZ state is this diagonal tensor. And when we say obtained, we mean via SLOCC, which is a paradigm in quantum information. It means stochastic local operations and classical communication. Here I wrote it down in a formula. So what do? You're allowed to take many copies of your GZ state, R times K plus little of K many copies, and you are transforming this into K copies of T. Yeah? The smallest R that you can put here, right? That's your most efficient rate, that's given by the asymptotic rank through this formula. Yeah? So you can think of this as some sort of cost. This term is brought up before, has been brought up. Okay, so that's one interpretation of the asymptotic tensor rank. The asymptotic subrank has the opposite interpretation. So here you have many powers you have a large power of your tensor T, and you try to transform it into a power of the GZ tensor, so as many as possible. Yeah, so here you're trying to maximize this rate R, and this relates to the asymptotic subrank. Okay, so that's subrank is the Gaussian elimination one. You're trying to distill a diagonal, so that's also kind of natural with this, right? It kind of matches what we're doing here. Yeah. Good. So that's kind of.
So the computational cost for these determining the ranks is that, Gaussian elimination for matrices is, fixed, easy.
Yeah.
You know what you're doing.
Yeah.
Okay. So when I do this other stuff, do I?
Yeah, that's a very good question. So the asymptotic guys, of course, are very complicated, but you can also already ask it for the subrank, and we don't know. That would be a question I asked at the open problem session, but it's already now.
What about the tensor rank? Is that efficiently?
The tensor rank is NP hard. That's known. Yeah. That's known. That's a result of Hofstad. Yeah. Yeah. Yeah, it's a good question, and I don't know. Many of these that many of these tensor parameters are NP-hard.
Okay, so the subrank could be easier, but no one knows.
Might be easy. I don't know.
Okay.
Oh, no, much better.
And actually, these two guys might also be easy. We also don't know. Yeah.
Which two guys, you said?
The asymptotic rank and the asymptotic subrank, we also don't know what their complexity, what their computational complexity is. Like they look complicated because we're doing this limit, but there might be an efficient formula.
Is there reasonably upper bounds on the asymptotic ranks in terms of complexity?
No. No.
Because the normal ones are kind of in NP. I can give you a certificate that the rank is at most something.
Yeah.
Or at least something.
Yeah, I agree. Yeah, definitely over finite fields. Yeah. Okay.
Are they computable? I mean,
I think we don't even know that. Yeah. These asymptotic parameters, yeah, it's the same for Shannon capacity of graphs. We don't know. Good question. So this is kind of the quantum side. There's other motivations for the asymptotic rank. It characterizes matrix multiplication complexity. That's kind of where it comes from. So here, we're trying to multiply two matrices, n by n matrices, and we're asking how many arithmetic operations are required to carry this out. So how many scalar multiplications and additions do I need to do to do a matrix multiplication? And this we denote with this omega. So this is the complexity. It's n to the power some exponent. We don't know what omega is. We know this complexity is between n squared and n cubed. That's kind of the trivial. These are the trivial bounds. This is called matrix multiplication exponent. What's known at the moment is that this omega is between 2 and 2.37, something like this. Yeah? And there's a lot of research going on in bringing this down. I guess people also think about bringing this up. Yeah. It's a very active field. How is this related to tensors? There's a tensor characterization of the complexity of this problem. It goes through this specific tensor. It's a family of tensors, matrix multiplication tensor for n by n matrix multiplication. It's this tensor. Doesn't really matter, but this is what it is. And what's the connection? The asymptotic rank of the matrix multiplication tensor, just for its size 2, so kind of the smallest one, equals 2 to the power omega. Yeah, so if you want to know omega, you can study asymptotic rank of this tensor. Good. Yeah, so it characterizes matrix multiplication complexity. And the central problem in this area is to determine whether this omega, this exponent, is 2, which is the trivial lower bound, but it's the best lower bound we have, or strictly bigger than 2. That's completely open. In other words, is the asymptotic rank 4 or strictly larger than 4? We don't know.
Is it clear that it's sufficient to look at the size 2 matrix multiplication tensor to answer that question?
It comes from the fact that all these matrix multiplication tensors, like you can approximate them with powers of this tensor. Like the idea is that if you want to multiply two large matrices, you can make them into block matrices and multiply them blockwise. That gives you this tensor power structure, and that's kind of reasoning that proves this.
So you're saying that's the most efficient way in which you can do it? Because couldn't it be that I want to see that's bigger than 4, but if I cut it in 3 by 3 blocks, I can do better or something like that?
No, but we're looking at asymptotics. We're looking at this matrix multiplication exponent, so it's like the asymptotic behavior.
Okay. It's the same tensor.
If you know this, you know the precise answer for 2 to the k by 2 to the k for all k.
Exactly.
And then you can interpolate for any n.
Exactly. So this would deal with...
Between some 2 to the k, 2 to the k plus 1.
Exactly. So it would deal with matrices of size 2 to the power, so some number k. That's sufficient. This we want to know, but there's something much more general that's open, namely, does there exist any tensor of size n by n by n, say, where the asymptotic tensor rank is strictly larger than n, the dimension it's living in? We don't know. We don't know any example. Yeah, so this is a generalization of this question. Okay.
Without the twiddle, we know.
Without the twiddle, we know.
Like the guy above.
It can be a little bit above. That's right. Yeah.
It can be n squared over root 3.
Yeah.
And that's, if you take a random tensor,
That's the.
it's roughly n squared over 3.
That's right. But then maybe you take this random tensor, then I start taking powers of the random tensor, and then it's not so random anymore. Yeah. Then we don't know what happens. Okay. That's 2. And then 3, like, it's a hard problem, so let's maybe zoom out a little bit more even. We can ask, and this is an open problem too, what is the structure, and then you can think geometric or topological, algebraic, whatever, of the set of all values that this asymptotic rank can take. Okay. So we're focusing on that question, and we can ask, yeah, what can we prove about number 3 without resolving 1 or 2? 1 and 2 are very hard problems, so what can we say about 3? And there's something that was already known, that's maybe a starting point, and that's this set of all these values that you get if you plug in all the possible tensors. This set is closed under applying any univariate polynomial with non-negative integer coefficients. So this tells you something like there's many values in this set. If you know some value, you can produce more values that are in this set. Yeah? Okay. That's known. Good. So this asymptotic tensor rank, we'll come back to this. Let me say a little bit more about asymptotic subrank and asymptotic slice rank. These have applications in combinatorics, like I mentioned, there's the slice rank method for cap sets, non-flower free sets. They also play a role in matrix multiplication, again, in a different way. One example is in barrier results for matrix multiplication algorithms. And here we can also ask, what is the structure of these sets of values? Yeah? The same kind of question as on the previous slide. And knowing this would give us information on the power of, say, the slice rank method. Again, what's known also here is that these sets, each of these sets is closed under applying these polynomials that I mentioned on the previous slide. All right, so far so good. Let's move to the next part. So what do we know? I'm going to focus now on the asymptotic subrank and the asymptotic slice rank. Here we can actually figure out what are the smallest values of these parameters. And they're these numbers. So 0, 1, 1.88, 2, 2.68. These are the smallest values that you get if you vary over all the tensors. You can plug in all tensors you like. You will not get any values in between here. Above here, we don't really know what the values are. There's some more results that were proven in recent years. People have proven that there's only, if you work over the complex numbers, there's only countably many values that you get for these two parameters.
For both.
Yeah. Over finite fields, the same group of people proved that the set of values that you get is well ordered, which means something like you have no accumulation points from above. Okay, so this was also known. So I will talk more about extending these results. I will say a little, like something short about how we get these values. It's in 2 papers. It's through a classification theorem. So it's not too important for the rest of the talk, but let me just say it so that you have some rough idea of how we prove such a thing. We take... No, it's not quite an entropy. It comes from some other solution to some equation. There's some entropies in there. There is an entropy in there, actually. Yeah. But it's not literally something like this. Yeah. Take a tensor, take it to be non-zero, then one of the following is true. And there's some cases that we get, and these cases give you these numbers. The first case is T has a flattening of rank 1. That means I have 3 legs, I group 2 of them together, and if I get a matrix with rank 1. In this case, you will get this value 1. Another case is that T is equivalent to the W state, which is this state, this tensor. Equivalent means equivalent under SLOCC. This leads to this number. Third case is that you can transform your tensor to a diagonal tensor. So the subrank is at least 2. And there's a flattening of rank 2. That gives the number 2. And the last case, a bit more complicated. Yeah, here you get that all flattenings of T have rank at least 3, and T either degenerates to a special tensor called the null algebra, or T is equivalent to some skew-symmetric tensor. It doesn't really matter what happens here, but I just want to point out that these numbers, so this leads to this number, they come from some sort of classification of tensors. Okay? Good, so that's what I wanted to say about these smallest values. And now I want to talk...
You go back for 1
Yeah.
second. So you're saying that if all flattenings of T have rank at least 3,
Yeah.
it either degenerates to this null algebra or
Yes.
it's equivalent to this
That's right.
skew
Yep.
tensor.
Yeah. Yeah. Exactly.
You,
It will be this.
Or you mean asymptotically equivalent?
No, it's just equivalent. So, meaning I can take linear combinations of the slices to get this tensor, and I can take linear combinations of this tensor to get this tensor. Linear combination of the slices.
But I mean, that is a very specific tensor, and
Yeah,
T can be very big.
that's right.
But he's saying either T sits inside C3, 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 and is equivalent to it, or it degenerates to the null algebra.
So here, a lot is possible,
It's
right?
basically,
Ah, okay, it's not
99
equivalent.
almost all of them degenerate to the null algebra, and there's just this one exception.
Okay, okay. So I should see
It's really weird.
1, 2, 3, and B as kind of special cases, and basically it's the A which is
Generic.
generic.
Yeah, that's right. And I didn't explain what this is, and I will leave it. I will not talk about it, but yeah. Okay. All right. That's that. I want to focus on the discreteness theorem, and I'm going to focus on one version of it, like a simple version. And that's for the asymptotic subrank. So here's the theorem. It's one version. I will explain some other versions later.
So that 2.68, then that was found by Strawson for that null
Yeah.
algebra.
This number
Yeah,
it comes from somewhere. Yeah, that's right. Yeah, yeah.
Okay.
Yes, exactly. Here's one version of the discreteness theorem. If you take over any finite set of coefficients S, yeah, so I take now a finite coefficient set because it's just going to make the explanation a bit easier. The set of possible values that the asymptotic subrank can take over all tensors with coefficients in S, but tensors of all possible sizes, is a discrete set. Okay? So let me just explain again what that means. Discrete means there's no accumulation points. Or in other words, any converging sequence must become constant, or the values are gapped. We know something about the gap. We know it's at most 1 over square root n. And we also get similar results for other parameters and other regimes, slice rank and tensor rank. Let me just mention, for example, for slice rank, what we get is a similar statement, but we get it actually over the complex numbers. Yeah, so here, if I take all the possible values of the asymptotic slice rank over all tensors with complex coefficients, it's a discrete set. Okay, good. So, how do we prove such a thing? I'm going to talk about some proof ingredients. I'm just going to talk about 2 lemmas here, which together give the proof of that theorem, the discreteness theorem. And the first lemma is about big tensors, and the second lemma is about thin tensors. So what is this first lemma? It says, if you take a tensor, I lost my pointer. If you take a tensor that's concise, we've seen the word concise before, means it doesn't fit into a smaller space, then the asymptotic subrank of the tensor is always at least cube root of the smallest dimension. And here, I'm not really assuming anything about the tensor, just that it's concise, but that's a very mild condition. It just means n1, n2, and 3 is really the size of the tensor. It doesn't fit into a smaller space. So that's the first lemma for big tensors. Second lemma says, okay, how about what happens if one of the dimensions remains constant? Yeah, then lemma 1 is not so impressive anymore because it depends on the smallest dimension. So one of these dimensions is constant, and say n1 is large enough, depending on this constancy. Then we prove that the asymptotic subrank, the asymptotic subrank actually becomes equal to this smallest dimension, this constant.
Even if n2 is 1? Because then it has slice rank 1.
So this tensor is concise. So what happens is that,
Tensors.
so if n1 is large enough, n1 is growing, then n2 must also grow.
Yeah, right. So n1 has to be like n2 times c or something.
That's right.
I see.
Yeah.
I see. So that's
Yeah, it's kind of hidden. If n1,
What's up?
if n1 is big, n2 must also be large. That is hidden in this conciseness condition. Okay. Yeah, a good question. Okay.
This is for generic tensors or for
Any tensors. Yeah, any tensors. That's kind of the surprising part. Yeah. We don't assume anything else. Yeah. Okay, now I have these two lemmas. Let's just assume that they're true, and let's see how we get the main result. This is a proof sketch. So I take some infinite sequence of such values, these asymptotic subranks, for some sequence of tensors. And these tensors, we may assume, are concise, and the dimensions are ai, bi, ci. Now, two things can happen. Either these dimensions, they all go to infinity, right? So that could happen. That's unbounded. So the minimum of the dimensions goes to infinity. Then, because of lemma 1, the asymptotic subrank must also go to infinity, right? Because I have this lower bound. So that's case 1. So in this case, we're definitely not converging. So we don't have an accumulation point here. Second case is, okay, we're not going to infinity. So let's say that the ci's have a maximum c. Then you can deduce that ai must go to infinity. We apply lemma 2, and we find that this q tilde of ti must become eventually constant. This follows. This you can prove with lemma 2. It becomes equal to the smallest dimension. Okay. So
what if ci is constant equal to c? Why can't ai and bi also be constant?
I take an infinite sequence.
You can have an infinite
But
sequence
with infinitely many
in
different
space.
values.
But you can have
Yeah,
an infinite
good, okay.
sequence in space.
Good question. And this is where I use that the set of coefficients we're working over, but I didn't write it here, that's actually a typo, is a finite set of coefficients.
Okay.
Yes.
Okay.
Thank you.
So you're
Thank you. This is what I use here.
Okay.
For slice rank, we don't need that. We do something else. Yeah. So, but there's only finitely many tensors of a certain format. You need to go up in format. Yes. Thanks. This is kind of the simple to explain version, so I can use this kind of fact here. Good. Okay, so that's how you combine these lemmas. This is all I'm going to say about this proof, actually. But I do want to say a little bit more about these two lemmas and some ideas of where these lemmas come from, especially the first one, actually. Lemma 1. So I want to talk, maybe I won't give the full proof of lemma 1, but I want to talk about some proof ingredient which I think might be of independent interest. And it's a very basic statement about matrix subspaces. So what do? You take a tensor, T, I draw it as a cube, you slice it up, you can do this in 3 directions, right? I get a collection of matrices. Here there are a collection of matrices, here a collection of matrices, and I take their span. So I have 3 matrix subspaces. And the property I want to study here, the property we need to study to prove lemma 1, is a parameter that I call Qi, which is the maximum rank in the span of such a collection of matrices. Yeah? So I look at the maximum rank in this span, the maximum rank in this span, and the maximum rank in this span of matrices. So I get these 3 numbers, these 3 max ranks. And these should be related to each other, right? These numbers, because these matrix subspaces, they're not just any 3 matrix subspaces, they come from a single tensor. And what we prove is indeed that there's this pretty strong connection. So it's this lemma. If your tensor T is concise, and you take any distinct directions, I, j, and k, so any permutation, any possible permutation of the numbers 1, 2, and 3, if you take this max rank in direction I, you multiply it with the max rank in direction j, it's always at least nk, so the dimension in the 3rd direction. Yeah? So these max ranks, they cannot both be small. Yeah? And I want to say something about how we prove this. So this is this is an important lemma for us. I think it might have used in other places. Let me say something about how you prove such a thing. It's pretty basic, actually. Proof sketch. We apply a random basis transformation to the tensor. That's kind of step 1. meaning I apply 3 random linear operations to the tensor legs. Okay? Then I take a certain slicing of my tensor in one of the directions, and let me just put these matrices next to each other. Then, because I have applied this random basis transformation, I may assume that the first R1 columns of this matrix, the first R2 columns of this matrix, R3 columns, etc., these columns together they're linearly independent. Yeah? So the linear independence among all these columns, they sit in the first couple of columns, and it's non-increasing. The number of linear independent columns is non-increasing. This you can do if you have applied this random basis transformation. That's step 1. Step 2 is you slice it in one other direction, and then you look at the first slice. And the first slice, you will see that these columns over here, they're actually the first column of each of these slices. They will sit here next to each other. And that's what happens if you slice in the other direction. So this slice has at least this number, so the number of indices such that Ri is not 0, many linearly independent columns. So what do we get? Q1, which is the maximum rank in this span, is at least R1, say. Q3 is at least this number, is at least the rank of this first slice. And so we get this inequality. And if you look at this product, so R1, which is the largest of the Ri's, and the number of non-zero Ri's, this must be at least the sum of the Ri's, which by conciseness must be N2, which is the dimension in the other direction. Okay? But that's how the proof goes. It doesn't really use anything. It's linear algebra. Okay. Good. So that's that lemma. Lemma 2, I won't say much. I will just say that instead of studying maximum ranks of matrices in like matrix subspaces, we study the minimum ranks, which is just the smallest non-zero rank in your matrix subspace. So we have to study this parameter, and we prove a relation between this min rank and the subrank, and we use some tensor power tricks. So those are the ingredients. Brings me to the end almost. So the general result, there's a couple of regimes that we cover. So I phrase it like this. We have discreteness of our set of values in the following cases. For finite sets of coefficients, we have it for these 3 parameters, so asymptotic subrank, asymptotic slice rank, asymptotic tensor rank. In fact, asymptotic tensor rank has a much simpler proof. This you can really prove using almost nothing. Over the complex numbers, we have discreteness for asymptotic slice rank. This proof is more involved because we cannot use this finiteness of the set of coefficients, so you really need to do more. And it uses moment polytopes, the fact that there are only finitely many moment polytopes for a given format of tensors, and quantum functionals. For arbitrary f, we also have a result for specific types of tensors, which I will maybe not talk about too much. That's a general theorem. Let me just end with some things we couldn't prove, some open problems. So remember this lemma 1 for big tensors, which said that the asymptotic subrank is always at least the cube root of the smallest dimension. We don't know if this is optimal. We don't know if this is optimal. So is this optimal? What we can prove is that for symmetric tensors, you can actually do better. So we get a square root lower bound for this asymptotic subrank. But even this, we also don't know if this is tight, in fact, for symmetric tensors. That's question 1. Question 2 is, what are the other values, the next values of asymptotic subrank? Higher order tensors, we don't really know how to deal with those. So order 4, order 5. That will require something new, probably. And arbitrary fields. So the asymptotic subrank result, we have it over finite sets of coefficients. But I think we do believe that this would also work over just complex numbers or infinite fields. We don't know how to do that yet. Good. That's it. Thanks.